So, good morning, good evening, good afternoon. My name is Gerald Pasquale, and I'm with the technical marketing team here at Park Systems. We are a leading manufacturer of atomic force microscopy systems and other emerging nanoscale microscopy techniques. It's my pleasure to see you guys log in early. Thank you very much. This morning, we have a very special webinar from the technical marketing team. Mr. John Paul Pineda will be presenting Electrochemical Atomic Force Microscopy from Park Systems today. And if you can hear my voice, hopefully I'm going out 5 by 5, loud and clear to all you guys. Your mics have been disabled by default, and that's by design. That's intended to give Mr. Pineda an uninterrupted speaking experience, but please do not let that discourage you from typing in your questions to us as they pop up in your heads. Because what will happen is in the control panel that has popped up on your screen when you logged in the session, there is a section, a module called questions. And from there, you can type in any question at all that you have for us. After the conclusion of Mr. Pineda's talk, we will then go back to the series of questions that we received. We'll answer them in sequence to the best of our ability. And for those questions that we won't be able to get to, don't worry, we will be able to follow up with you via email. So without further ado, I'm going to go ahead and turn things on over to Paul. Paul, can you hear me?
Yep, I can hear you clearly, Gerald. Hello, everyone. Again, good morning or good afternoon or good evening, depending on where you are. My name is John Paul Pineda, and I'm from Technical Marketing Group here at Park Systems. And today it is my pleasure to give a short presentation about Electrochemical Atomic Force Microscopy, or EC-AFM, provided by Park Systems. So without further ado, I'm going to go ahead and proceed with my presentation. So basically, the focus of my presentation is to demonstrate the experiment we have conducted using EC-AFM and the setup of that experiment. But before we proceed to that, let me just share with you some of the application of EC-AFM. So in recent years, understanding electrochemical processes of various materials for the purposes of things like battery development or fighting the effects of corrosion have become a commonplace. So it is through the improvements of special techniques like electrodeposition that we started to make breakthroughs, like in fighting things such as corrosion. So for those of you who are not familiar with electrodeposition, it is a process that utilizes electrical current through a solution with electrolyte to modify surface properties. So here on the lower left corner, we have an electroplating facility that is basically a form of electrodeposition. And the modification of surface properties, let's say a sheet of metal, either through chemical or physical means, they make the material or the metal sheet more suitable for certain application. Like, for example, withstanding maritime conditions, or withstanding corrosion or rusting in salt air breeze for metal structures next to an ocean. So in the lower right, we have an example of the electroplating bath. So based on the principle of electrolysis, electrodeposition uses electrical current to reduce the cations of a desired material from an electrolyte and coat those materials as a thin film onto a conductive substrate surface. So this technique is commonly done to enhance electrical conductivity, and it is also done to improve corrosion resistance, as I mentioned earlier. And sometimes it is used to make products more aesthetically appealing. So given that good deposition mainly depends on the substrate surface morphology, So a technique that can measure this characteristic and monitor electrodeposition process in nanoscale is greatly needed. All right, so to overcome these shortcomings of ex situ techniques such as SEM or slower techniques like STM, electrochemistry has been combined with atomic force microscopy, and EC-AFM has been introduced by that time. So this technique allow users to perform in situ imaging and visualization of changes in surface morphology of the sample being studied under a certain electrochemical environment in nanoscale. So in our experiment, the deposition and the dissolution of the copper particles into the gold surface was successfully demonstrated. So the morphological changes of the copper particles was clearly observed in situ using our new Park NX10 AFM. And a current voltage or CV curve was simultaneously acquired using the potentiostat, which we actually combined with the system during the experiment. All right, so let's talk about the experimental setup. So here we use a liquid probe hand shielded with glass instead of the conventional probe hand, just to allow measurement in the liquid. So a nanosensor point probe plus contact coated with platinum and mounted on Teflon chip carrier was used in the experiment. So we use platinum coated cantilever just to maintain the beam intensity when the tip is immersed in the solution. And the tip was mounted on a Teflon chip carrier to protect the EC cell from other unwanted electric signals that could actually affect the condition of the electrolyte solution. So the deposition and dissolution of the copper particles onto a thin film of 111 orientation was monitored again using a Park NX10 system. And also in the experiment, a reference image of the gold surface was acquired in ambient air and in liquid condition without introducing chemical reaction, just to serve as a point of comparison of the sample surface before and after the experiment using non-contact AFM. So after obtaining the reference image in liquid, the 3 electrode was connected into the potentiostat. So the counter electrode and reference electrode was bended before immersing in the liquid, just to make a good contact and prevent saturation of the signal. So here in the experiment, a silver chloride electrode was used as reference electrode since a chloride solution was not used. So if in case you guys will use chloride solution, other type of electrodes such as mercury or mercurious sulfate can be used instead. And then for platinum iridium electrode, we selected this one as a counter electrode since this material is chemically stable. Therefore, it will not contaminate the solution. So this is just an overview of the electrochemistry cell that was used to house the electrode. So the solution as well as the sample in the experiment. So just to give a point of reference, if you guys have never seen the sample stage of small sample AFM before. So this EC cell, it can actually fit in the palm of your hand. So that should give you a reference to how big this cell is. So in this particular EC cell that you see here, this is something that we manufacture and provide to customer who purchase an EC-AFM option. Also, here the EC cell polychlorotrifluoroethylene is the material that we choose to make this EC cell, just to ensure chemical stability. So a sample is mounted with a top cover and sealed with a thin silicone O-ring to securely prevent leakage. The working electrode that was used here in our experiment is a gold thin film. So it's about, I think, 150 nanometer thick, and it is evaporated on a mica surface, while the reference electrode and the counter electrode, as I mentioned earlier, are silver chloride and platinum iridium. So the three electrodes were actually connected on a Solartron Modulab XM ECS potentiostat. So this is the model of the potentiostat that we use in the experiment. And the aqueous solution contained around 0.1 millimolar of copper sulfate in 50 ml of 0.01 millimolar of sulfuric acid. So in this experiment, we added sulfuric acid to the solution just to stabilize the copper and to prevent precipitation during chemical reactions taking place. So this figure just shows you the CV curve that we we obtained during cyclic voltammetry. So we ran 4 complete cycle of oxidation and reduction process, or redox process. Here you can see the CV curves that we have collected are quite overlapping to one another. So if you will analyze the results, you will realize that the redox process are reversible depending on the amount of potential applied on the solution. So the CV curve also shows that in negative 0.1 volts, the solution is in neutral state wherein no chemical reaction is taking place. So the section of the CV curve at around this voltage is the horizontal line you see in the middle of the curve. All right, so as for the redox process, let's take a look at each half of it. So in EC-AFM, the working electrode is the sample surface where the electrodeposition process took place. So in this case, it is the gold circle on the middle of this image. The counter electrode indicated by the red line is where the electric current is expected to flow. So in case you guys are new to electrochemistry, this EC cell is basically like an electronic circuit. And the main function of the counter electrode here is to close the current loop in the circuit. And the reference electrode indicated by the blue line here is used as a fixed reference point. And it serves as a feedback to maintain a stable voltage in the solution. So for example, if you wanted to sweep to negative 0.2 volts, it allows the system to maintain an equilibrium of around negative 0.2 volts. So in this system, an electrical field is supplied in the working electrode to transmit electrons to ions in the solution. So here we have the copper sulfate, and the type of chemical reaction depends on the amount of the type of voltage supplied, so either positive or negative voltage in the cell. So if we wanted to induce reduction, so we just need to supply a negative voltage in the cell. So in our experiment, we performed the sweep from negative 0.2 volts to negative 0.4 volts. So what we saw is the reduction of copper. When that occurs, the copper disassociates with the sulfate and it settles on the surface of the gold thin film. So we actually did this cycle more than once, which we will be seeing on the succeeding slides, where more and more copper particles were electrodeposited on the gold surface. All right, so for oxidation, it's quite similar with the reduction process. So the only difference is that we are applying voltage in positive direction, or we are applying a going to positive voltage. So in this example, we sweep from negative 0.2 volts to 0 volts. All right. So when that occurs, the copper begins to vacate the gold surface and begins to reassociate with the sulfate to reform a copper sulfate in the electrolyte solution surrounding the electrodes in the cell. So when the positive sweep occurs, more and more copper leaves the gold thin film surface. And what we will see on the subsequent AFM image is that the gold thin film surface comes from being clean to being crowded with copper particles, then back from being clean again. And this indicates that the CV curve I have shown earlier is totally a reversible process. So here we have the reference image we took while the gold sample is submerged in the solution. So here you can see a 2 by 2 micrometer image of the sample prior introducing electrochemical reaction in the solution. So as you can observe, the gold surface is made of crystal terraces. And as you can see, there are no foreign particles present on the gold surface prior electrochemical reaction to place. So now, after we took that reference image, we started to apply a negative linear sweep voltammetry to the solution. So as I mentioned earlier about negative 0.2 volts to negative 0.4 volts, dealing with a scan rate about 10 millivolts per second. So after we run the first sweep for about 20 seconds, we took another AFM image of the sample surface. And that is what you can see here on the left. If you will compare the reference image to this image, there is a clear difference between them. So as you can see, there are particles deposited on the gold surface, and we are starting to see small circular areas with brighter contrast compared to the gold surface. So this one indicates that these particles are resting on top of the gold surface. So by the way, brighter region on this image, it indicates a higher surface. So then we did a second sweep, and we used the same parameter as the first sweep. As you can see on the AFM image we took here, more particles were deposited on the gold surface on the second sweep. So we just run 2 sweep to cover the entire 2 by 2 micrometer surface of the gold sample with the copper particles. So at some point there's some kind of a threshold that we can observe here. So where the copper just move into mass to deposit themselves to the gold surface. Now let's proceed with the oxidation process, or the removal of the copper particles. As I mentioned earlier, we just need to apply a voltage in opposite direction. So from this time, we apply from negative 0.2 volts to 0 volts to induce oxidation. So except for the voltage we applied, all of the parameters we use here are the same with the reduction process. So here, the magnitude of the copper dissolving on the gold surface will increase as more and more positive potential is applied in the cell. So after the first sweep in the reduction process, we are now starting to see that some of the copper particles were removed, but still we cannot see the crystal terraces of the gold, since majority of the sample surface is still covered with these copper particles. So we run again a second sweep with the same sweeping condition, and now we are starting to see more areas of the gold surface. But still, there are copper particles visible on the sample surface. So when we run again another sweep with same condition, and this time majority of the copper particles were removed, and we are starting to see a return on what we are expecting to see from the reference image, which are these crystal terraces of the gold. Then finally, we run the fourth and last test with same condition. This time, we got an AFM image of the gold surface, which is essentially clean and free from copper particles. And now we can clearly observe the crystal terraces of the gold surface. All right, I just want to draw your attention back again to the CV curve that we have acquired with the potentiostat. Again, a 4 complete cycle of oxidation and reduction was performed. For reduction, we did 2 linear negative sweeps. And for oxidation, we did 4 linear positive sweeps. So it took a little bit more tests to remove the copper particles off the sample surface, but eventually we have successfully removed them all on the gold surface. So the results we acquired in the experiment just simply implies that the redox process are reversible depending on the amount of voltage or potential applied in the solution. So just to give you a summary on what we did on the experiment. So first, we took a reference image, as you can see on the left image. Then we deposited copper particles in the gold surface, as you can see on the AFM, on the middle of the AFM image. And then we removed the copper particles back into the solution, and we got a surface which is pristine as the reference image, indicating that, again, this process is completely reversible. So this simple experiment, I just want to mention to you again, we have done this using our new Park NX12, which is equipped with EC-AFM option. All right, that's pretty much it. Thank you very much for your time and listening.
Thank you very much, Paul. So that was a look into electrochemistry on the Park NX AFM platform. As it says here on the slide, if you are curious about the hardware and also the supporting software to run such an experiment or any other electrochemical application, please visit us at parkafm.com. I'll go ahead and leave a link to our company website in the chat so that you guys can visit it after today's session. So we have now arrived to the portion of the talk where we will be fielding questions from you guys. So I'm going to give everyone here a couple minutes to digest the information that Paul presented, and we'll be handling questions through that module here in the control panel. So go ahead and send some in. We'll be happy to answer what we can here live on the air. While we're waiting for questions to arrive, just a couple of announcements in terms of upcoming webinars. Our next webinar is going to be this